Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight, something curious drifts toward us, slow and indifferent to our attention. Far from the chaos of city lights or the rumble of human urgency, a visitor from deep space is drawing near. It moves without sound, fragmented and faint, and yet it multiplies. This visitor is known as 3I Atlas, a confirmed interstellar object, and only the third ever recorded of its kind. Now, as it approaches the quiet presence of Mars, new companions seem to appear in its wake. The sky grows more populated, more subtle, more filled with questions. It's a story of cosmic choreography, of fragments unspooling across space, like soft threads tugged by gravity's invisible hand. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. And if you're listening from somewhere under soft blankets, or maybe nestled in a quiet room beside an open window, feel free to let us know where you are and what time it is where you are. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. The object we now call 3I Atlas was first detected in late 2023. Its trajectory didn't quite fit the usual patterns. Astronomers noticed that it was travelling just a bit too fast, on a path too steeply inclined for a regular solar system comet. And most notably, it wasn't bound to the Sun. Its arc was hyperbolic, a trajectory that would carry it in and then back out again, forever leaving behind the planets, moons, and dust that orbit our familiar star. That path, curved just enough to whisper, "not from here," earned it the classification of an interstellar object. The 3I marks it as the third known visitor from beyond our solar system, after Oumuamua and Borisov. The name Atlas honours the survey system that first caught sight of it, the Asteroid Terrestrial Impact Last Alert System, designed to catch celestial objects on potentially hazardous or curious paths. But something new has emerged around 3I Atlas, adding a fresh layer to its mystery. As it approached Mars's orbital region, astronomers began to notice what they call a debris train, a line of small, newly observed objects trailing behind it, or perhaps orbiting in loose association. Not large enough to be comets themselves, yet distinct enough to be tracked. The implication? Fragmentation. But also multiplication. Objects like 3I Atlas may fracture under thermal stress, tidal interactions, or previous encounters with other bodies long before they reach us. The idea that we might now be seeing the result of such past fractures feels oddly intimate, like catching a snowflake mid-melt, already splitting but still holding form. These new fragments reflect sunlight gently, casting soft trails that may linger behind or veer slightly away, depending on their mass, spin and position within the gravitational environment they now enter. Mars, with its own subtle gravity and two quiet moons, Phobos and Deimos, sits not as a barrier, but as a participant in this slow dance. Its thin atmosphere and small mass offer little resistance, but its presence nonetheless shapes the local space. There are regions like its Lagrange points where gravitational balances might temporarily host small debris. We'll drift into those later. For now, we stay with 3I Atlas itself. It's faint, barely more than a dot to our most sensitive instruments. Yet its presence draws in our imagination. It invites questions. Where did it begin? Was it ejected from a distant stellar nursery, flung from the outskirts of an ancient system's planetary disk? Perhaps it wandered for millions, even billions of years through interstellar space, untouched, unlit, unchanged until now. The very fact that we can see it at all is an accident of timing and light. Sunlight, weak as it may be at that distance, reflects off its surface. That light, travelling at a calm and constant pace, finds its way into our telescopes. We measure its motion against the background stars and calculate a path. From those numbers we infer an origin, not precise but probable. It didn't come from our local system. Its speed is too great, its trajectory too steep. And yet, it has entered our story. Astrophysicists still debate whether interstellar objects like this are rare or simply hard to detect. Are we just at the beginning of discovering a larger population of tiny transient visitors? The sky is vast. Our instruments see more than they once did, but still only a fraction of the faint bodies that might pass silently between the stars. Perhaps comets like 3i Atlas are everywhere, flickering in and out of our solar neighbourhood, but noticed only when chance and angle align. This moment then, this season of approach, offers a brief window, a chance to observe, to wonder, to map and model. And for us, it offers an opportunity to drift alongside something truly ancient. Not just old in terms of years, but old in context. This object may have left its home system before our sun had planets. It may have floated in silence through deep interstellar night while Earth was still molten and wild. Now it curves past Mars. Fragments multiply. Light reflects. And we, watching from our own orbiting cradle, feel that familiar hush, the kind that lives between discovery and certainty. We drift now from the present moment, where 3i Atlas glides near Mars, into a much older silence, one that predates stars, one that lingers still if we listen closely enough. There is a kind of resonance between this lonely interstellar object and the ancient light that has filled our sky since the beginning. When we gaze into the dark, we're not only watching comets or planets or stars, we're also watching photons. Some of them are unimaginably old, older than our world, older than the stars that surround it. These ancient photons began their journey shortly after the universe became transparent, during a moment we call recombination. That moment, over 13.7 billion years ago, marked the end of the universe's first great fog. Before that, the cosmos was a hot, dense plasma, filled with free electrons and protons constantly scattering photons in all directions. Light couldn't travel far, it was trapped, bouncing endlessly. But then, as the universe expanded and cooled, protons and electrons combined to form neutral hydrogen. The fog lifted. Light began to move freely for the first time. This is the origin of the cosmic microwave background, the quiet glow that bathes all of space, a relic of recombination, stretched into microwaves by the slow, steady expansion of the universe. These photons have been travelling ever since, undisturbed, bearing the imprint of that first great transition. Now, as we observe 3i Atlas, we do so in the same light. The instruments that measure its faint tail, its dusty debris, and its shifting arc are bathing in the same ancient photons. There's a poetry in that. The newest fragment in our sky is framed by the oldest light we know. Perhaps you can imagine it. A dark sky, faint stars above, and somewhere within that blackness, a tiny point. Not brighter than a nearby star, not easily seen, but there, real, moving, its path silent, its origin foreign. And all around it that subtle microwave glow, invisible to our eyes but constant, a cradle of ancient radiation carrying stories far older than comets. It might seem strange to connect an icy object near Mars with an era so distant that no galaxies had yet formed. But in cosmology, scale folds in on itself. What's near is often shaped by what's far. What's small may echo what is vast. In that spirit, we notice how the soft fragmentation of 3i Atlas, its multiplying trail of new objects, mirrors, in miniature, the way photons multiplied in the early universe. Not by breaking apart, but by being released into a space suddenly ready to carry them. And just as the early cosmos was full of drifting light, so too is the modern sky full of drifting debris. Asteroids, comet fragments, icy cores flung from distant systems. Many of them small, many of them unseen, but all of them caught, at least for a moment, in the same gravitational weave that once shaped the first atoms. Astrophysicists still debate whether we're seeing the full picture of the interstellar population. 3I Atlas is only the third object we've labelled as such, but statistically, it seems likely there are many more. Perhaps hundreds passing through the solar system every year, too faint or too fast to notice. It's uncertain how many of them might fragment like this one. It's also unclear whether these fragments might reveal anything about the systems they came from. Still, we observe. We trace their trails, we model their orbits, and with each fragment that appears, each soft glimmer near the path of 3 Atlas, we extend our quiet map of the interstellar. There's something deeply calming about that process. Slow observation, gentle accumulation, no rush to conclusions, just a soft unfolding of evidence, like petals opening in morning light. You might picture a radio dish beneath a quiet sky, tracking a moving speck of dust thousands of kilometres away, or a wide-field telescope watching for the faint shift of a shadow across distant stars, or simply your own imagination, floating with this comet and its companions as they approach Mars's path. In some ways, these fragments are like seeds. They don't grow, but they carry within them a kind of memory, material forged around stars we'll never see. They drift past our world, unchanged by our presence. But for a moment, they are here. Their trails cross our sunlit sky. Their stories flicker across our instruments. And that, in itself, feels like a gift, a quiet meeting across unfathomable time. So we linger here, just for a while longer, between the glow of ancient light and the hush of multiplying fragments. The sky above is vast and still, but within that stillness things are moving, unseen forces are at work, and we, from our small orbiting planet, simply watch. If we let our thoughts drift even further back, beyond recombination, beyond the glow of ancient photons, we arrive in a darker stillness, a time before any starlight had formed, the cosmic dark ages, after the universe became transparent and the first atoms settled into silence. There followed a long, quiet stretch. No stars yet, no galaxies, only hydrogen and helium adrift in vast clouds, cooling slowly, slowly. This was a time before light had structure, before gravity had sculpted matter into the luminous forms we now see in the sky. We often imagine the early universe as an explosion of activity, a burst of creation, but in truth, much of its early history passed in silence. During the Dark Ages, the universe expanded under its own momentum, nearly uniform with only the tiniest fluctuations in density. Those slight ripples, so subtle they're barely measurable, would one day give rise to all the galaxies, stars and planets. But at the time, they were just whispers in the hydrogen fog, and in that hush, the first seeds of motion began. We think of 3I Atlas today, quietly approaching Mars not just as an object, but as a continuation of that early motion. It is matter that has remembered how to move. Perhaps it formed around a distant star long extinguished. Perhaps it was born in a distant ancient disk, then cast away by a planet we'll never see. Or maybe it was always adrift, matter that never quite joined anything, but instead wandered the deep between the stars. In this sense, the journey of an interstellar object like 3I Atlas feels like a story written in lowercase letters. No dramatic flares, no blazing tails like those of sunbound comets. Just a slow, persistent line, arcing across a dark canvas. And yet, the Dark Ages were not entirely still. In that early cosmos, neutral hydrogen sometimes clumped more densely in places, ever so slightly. Those clumps would eventually collapse under gravity's patient hand. But before that happened, they left a mark, a trace in the cosmic web, filaments of matter stretching across unfathomable distances, visible to us now only through the careful measurement of redshift and spectral lines. One such marker is the 21 centimetre line. It's a signal emitted when the spin of a hydrogen atom's proton and electron align, then flip. A quiet, precise signal. During the Dark Ages, this line was emitted everywhere by clouds of neutral hydrogen drifting in the void. It's still travelling toward us now, stretched by time and distance, like a whisper from across eternity. It's uncertain how much of this ancient hydrogen remains untouched. Some of it may still float between galaxies, dark and cold, never pulled into the gravity wells of forming stars. Perhaps 3I Atlas passed through such regions. Perhaps it carries traces, tiny fingerprints of interactions with primordial gas. We don't know, of course. Our instruments can only reveal so much. But it's possible that the body of 3 Atlas, its icy surface, its composition, records memories from these vast silent spaces. If so, each fragment that now trails behind it is like a shard of memory. A reminder of places too distant to map and times too old to count. Astrophysicists still debate what these dark ages were truly like. Some models suggest they were colder than we once believed. Others propose that small pockets of warmth, perhaps from dark matter interactions or faint early stars, began to light the edges sooner than we thought. But in general, it remains one of the quietest, most mysterious chapters in the history of the cosmos. And maybe that's why it resonates so strongly with this moment. With 3I Atlas gliding through the Martian neighbourhood, leaving behind a trail of faint companions. There is something deeply similar in their character. Quiet, dim, unrushed. The kind of thing you almost miss unless you know how to look. There's beauty in that, we think. A kind of humility. These are not the blazing supernovae or the dramatic jets of quasars. They are the slow motions, the long games, the subtle traces of a universe still unfolding. You might picture it as a long exposure photograph, stars smeared across the sky, light building gently on a dark frame. And in that stillness a single comet fragment drifts across the field, its path so soft, so slow, it leaves barely a trace. And yet, that trace is everything. From our small blue world circling the sun alongside Mars and the rest, we catch glimpses of these quiet visitors. Each one tells us that the cosmos is still full of surprises, that even in a sky we've studied for centuries, new objects can appear, new paths can be revealed, and just as the Dark Ages slowly gave way to the first stars, so too do our quiet nights give way to light, first with the morning and sometimes with discovery. So we watch. We trace 3I Atlas and its trail. We listen for signals from the past, and we remember that silence is never truly empty, not in the universe, not in us. From that ancient hush, there came a moment of quiet ignition, the cosmic dawn. It didn't happen all at once, no switch was flipped. Instead, in the vast silence following the Dark Ages, scattered regions of gas slowly collapsed under gravity's gentle insistence. The first stars were born, not blazing giants like our sun, but immense, short-lived metal-free beacons. They lit the void with a kind of light the universe had never known. The cosmic dawn was the era when starlight began to flow freely again. These early stars, sometimes called population 3 stars, were made almost entirely of hydrogen and helium. No heavier elements yet. Their lives were brief, just a few million years, but in that time they illuminated their surroundings, began to shape space, and seeded the first waves of cosmic structure. In a poetic sense, you could say the universe began to see itself during this time. We can't directly observe these first stars yet. They're too far, too faint, and too fleeting. But we can see their fingerprints, faint shifts in the hydrogen fog, glowing bubbles of reionization, and the earliest galaxies clustering in strange lopsided patterns. The James Webb Space Telescope has taken some of the first steps toward glimpsing these early lights, but there's so much still unknown, and now, in our own sky, we have another kind of light, 3E Atlas, and its quietly multiplying companions. They are not stars, of course, not even close. They emit no light of their own, but they reflect it. They catch the sun's photons and scatter them, just enough for our instruments to trace. In a way, they echo that early moment of re-illumination, not with brilliance, but with presence. The comet's soft glow near Mars feels like a distant cousin to the dawn, not in scale, but in symbolism. A quiet arrival, a first light after a long slow drift, and as it fragments, its pieces catch light. 2, each one a faint reflection, a subtle point of brightness against the black. The multiplication of objects around 3I Atlas is not an explosion, but a gentle unfolding. It reminds us of how complexity arises from simplicity, how one cloud of hydrogen became a star, how one star seeded a galaxy, how one galaxy gave rise to planets, and eventually to us. Even now, as we observe from Earth, we live in a sky still touched by that first dawn. The light from the earlier stars continues to travel, faint and stretched, altered by redshift and time, and alongside it, new light is constantly born. From young stars, from flickering nebulae, from distant supernovae whose shockwaves may eventually send more comets drifting through the cosmos. It's uncertain whether 3I Atlas was formed in a system lit by stars like those first ones. Its composition may tell us something about its origin. Icy, possibly rich in organic molecules, its surface marked by exposure to interstellar radiation. But without a close-up view, we can only guess. Its trajectory tells us where it's going. Its light tells us what it reflects. But its story is still cloaked in distance. Still, the poetic connection lingers. The cosmic dawn was an era of quiet multiplication. One star became many. One point of light became a sky full of them, and now, with 3C Atlas, we observe the same kind of gentle increase. One object arriving, then 2, then more. Like snowflakes caught in slow motion, astrophysicists continue to ask what conditions were necessary to end the Dark Ages. What tipped the balance from stillness to light? What distribution of matter? What small fluctuations were needed to birth the first star? And now, we might also wonder, what forces shape the fragmentation of a comet? What stresses cause it to multiply? What subtle gravity or pressure pushed it to split? In both cases, the answers are hidden in softness. Not violence, not suddenness, but slow, inevitable change. The kind that whispers more than it speaks. You might picture the early stars flickering to life over millions of years, their light expanding like ripples in a pond. Or the fragments of 3I Atlas trailing behind it, glinting one by one, barely distinguishable from stars unless carefully measured. Both are part of the same story, of a universe that builds slowly, patiently, from the simplest elements. And somewhere within that story we find ourselves, watching, listening, floating on a world that orbits quietly through light both ancient and new. We don't need to fully understand the cosmic dawn to feel its presence, just as we don't need to fully explain the fragments of a comet to sense their significance. Sometimes the wonder lies in the witnessing, so we let the early light drift through us, and we let the objects multiply. The universe rarely moves in straight lines. Its motions are curved, woven, and nudged, often gently, by gravity's unseen hand. And tonight, as we float quietly with 3 Atlas and its multiplying trail, we turn our attention to the small forces at play. The gravitational nudges that guide and sometimes fragment the objects drifting through this part of space. You might imagine a comet as a solitary traveller, moving in a wide arc around the sun. But in truth, it is constantly responding to the push of solar radiation, the pull of nearby planets, the faint gravity of countless other bodies. It doesn't fall so much as it flows. And sometimes, those flows divide. This process, called tidal fragmentation, occurs when an object passes close enough to a planet or star that its own gravity is no longer enough to hold it together. The larger body pulls harder on the near side than the far side, stretching the object until it splits. The result? A slow scattering of fragments along its orbit, often in a gentle curve. It's possible that 3I Atlas is undergoing just such a process now. As it approaches the region near Mars, astronomers have noticed several small objects appearing along its trajectory. These may be daughter fragments, pieces broken off from the main body, still moving with it, still reflecting sunlight. Their brightness is low, but consistent. Their paths, though slightly varied, are coherent enough to suggest a common origin. And this multiplication feels familiar. The universe has always multiplied itself in quiet ways. A single clump of gas in a primordial cloud collapses and becomes two. A star forms planets. A supernova seeds new stars. A galaxy merges and divides. Even now, the Milky Way is drawing in satellite galaxies with slow, tidal grace, stretching them, unravelling them into streams. One such stream, the Sagittarius dwarf tidal stream, wraps around our galaxy like a ribbon. It's the remains of a smaller galaxy being pulled apart star by star. These stars continue to orbit the Milky Way, but no longer as part of their original whole. They've been scattered, yes, but still held by a shared trajectory. So too, perhaps, with 3I Atlas. Its pieces may no longer form a singular object, but they remain part of a shared story. And their presence invites deeper questions. What stress caused the separation? Was it thermal, from the sun's warming light? Was it mechanical, from internal flaws or past collisions? Or was it tidal, influenced by the cumulative pull of Mars, Jupiter, or even distant Saturn? Astrophysicists still debate the relative impact of these forces on small interstellar bodies. Some suggest that comets like 3I Atlas are loosely bound to begin with, a kind of porous collection of ice and dust, more like a snowball than a stone. If so, even subtle gravitational fields could lead to splitting. Others propose that fragmentation might occur before entry into the solar system, triggered by collisions or stress accumulated over eons of drift through interstellar space. What is clear, though, is that these new objects, these small companions, do not appear randomly. They cluster, they move with purpose. Their brightness changes over time, but their motion suggests unity, and in their quiet multiplication, they offer us a fleeting glimpse of celestial process. Perhaps you've seen time-lapse videos of comets fragmenting, those sped-up visuals where small dots peel away from a central body, trailing behind like sparks from a slow-motion firework. Now imagine watching such a scene in real time. No rush, just a slow, unhurried unravelling. From Earth the sky seems static. Stars appear fixed. The moon rises and sets with dependable rhythm. But beyond that visible stillness, the cosmos is full of slow motion. Fragments move, orbits shift. Tails drift, all beneath a sky of ancient light. If you looked up tonight and could somehow see the space near Mars magnified 1,000-fold, you might notice it too. A cluster of barely visible points, each moving fractionally, each reflecting sunlight with a faint shimmer. They would look like nothing to the untrained eye, but to those who know what to seek, they would reveal a dance, a drift, a multiplication. And it's not only gravity that sculpts them. As we'll see soon, sunlight itself plays a role, gently pushing on the fragments through a process known as radiation pressure. Even light has weight in a sense, and over time, even that whispering force can change a path. But for now, we stay with gravity, the quiet sculptor, the constant weaver. It doesn't speak in sudden shifts, but in soft arcs and curved lines. It is gravity that draws 3I Atlas inward, even as it prepares to release it again. It is gravity that shapes the trails of fragments, holding them together while letting them drift. You might think of it like a lullaby with no beginning and no end, just motion, rhythm and return. And in that motion, we remember that nothing in the universe is truly alone. Even a lone fragment lost from its parent still follows the curves of space, still belongs to a larger path, so we watch, we model. We let our thoughts drift with the pieces of 3i Atlas as they multiply, not in chaos, but in quiet accordance with a cosmic tide. As we continue to drift with the fragments of 3i Atlas, our gaze shifts to a quieter region of the solar system, one not often considered in nightly stargazing, but full of quiet wonder. These are the Trojan points, the hidden pockets of stillness that ride alongside planets, including Mars, on their journey around the Sun. To understand Trojans, we must first visit a concept we touched on before, Lagrange points. These are specific locations in space where the gravitational forces of two large bodies, such as the Sun and a planet, balance perfectly with the orbital motion of a smaller object. It's a kind of cosmic cradle, where a fragment or asteroid can remain, not drifting away or falling in. There are 5 Lagrange points for every planet-star pair, and 2 of them, L4 and L5, form equilateral triangles with the planet and the Sun. These 2 points, situated 60 degrees ahead and behind the planet's path, are where Trojans are found. Mars has Trojans. Not many, not compared to Jupiter, whose Trojan clouds contain thousands of known asteroids. But Mars's L4 and L5 points quietly host a small group of stable companions. They drift along with the planet in its orbit, caught in a gravitational eddy, moving gently in synchrony. And now, with 3i Atlas entering the region near Mars, we wonder, might some of its fragments settle there? It's not impossible. A fragment travelling at just the right speed, arriving at just the right angle, could become captured. Not permanently, but for a time. It would appear to drift ahead or behind Mars, locked into a quiet loop, neither approaching nor retreating, just staying. Astronomers have theorized that these Trojan regions may be more than just parking spots for asteroids. They could act as collectors, gravitational basins where debris accumulates over time. It's uncertain how many of these bodies are native to Mars's Lagrange points, and how many may be interlopers, caught temporarily and then released again. In the case of 3i Atlas, we don't yet know whether any fragments are headed directly into those pockets. But we do know that the region is being watched closely. Wide-field surveys and infrared scans are keeping gentle track of any small objects whose orbits echo the Martian path. And if new, untracked bodies begin to appear near those Lagrange zones, it could offer a clue. Perhaps even now, a tiny ice-coated shard is curving into Mars's leading point, slowing slightly, entering a gravitational rhythm. If so, it might remain there for decades, or millennia, quiet and undisturbed, bathed in sunlight, reflecting a silent whisper back toward Earth. What's curious is how hidden these Trojans often are. They don't shine like comets or move swiftly across the sky. Their motion, relative to Mars, is slow. From our perspective, they barely shift. Detecting them requires patience, persistence, and subtlety. Still, some have been found. One of Mars's most well-known Trojan companions is named Eureka. It was discovered in 1990 and orbits near Mars's L5 point. Since then, a handful of others have been identified, including some that appear to be part of the same family. Fragments, perhaps, of a much older object that broke apart long ago. Astrophysicists still debate how stable these Trojan objects truly are. Some simulations suggest they can remain in place for billions of years. Others imply that minor perturbations, perhaps from Jupiter's distant pull or even from the Yarkovsky effect, where sunlight subtly alters an asteroid's path, could eventually send them drifting away. But for now, they linger. Quiet companions in a quiet sky. And we wonder if 3i Atlas will leave behind such a companion, an unnoticed piece, faint and slow, tucked into one of these gravitational alcoves waiting to be discovered years from now. There's something comforting about the idea that in a system full of motion, there are places of balance, that even fragments scattered and alone may find rest. And that rest isn't always permanent, it may be fleeting, but even so, it holds meaning. You might picture Mars on its endless loop around the Sun, trailing a thin wake of dust followed softly by a few quiet stones, some native, some adopted, all drifting in step, held by nothing but balance and time. And if we were to watch from above, high above, we might see those Trojan points like eddies in a cosmic river, places where the current swirls gently, slowing debris and letting it settle. Perhaps one of 3i Atlas's fragments will join that swirl, perhaps it already has. So we keep watching, we model possibilities, we wait for small flickers in the data, because in astronomy, even a flicker can tell a story, and in this case, the story might be of a fragment from another star system, slowly falling into step beside a red planet, under a velvet sky. The Lagrange points, those quiet balances where gravity and motion cancel one another out, are not just abstract coordinates. They are real, measurable, and sometimes beautifully still. As we drift gently with 3i Atlas and the fragments that trail it, we find ourselves brushing against these pockets of cosmic equilibrium. For Mars, as for any planet orbiting the Sun, there are 5 such points. We've already wandered through the L4 and L5 regions, those triangular positions ahead of and behind the planet, where Trojan asteroids may drift serenely. But the other 3 points, L1, L2 and L3, form a more delicate alignment. They sit along the straight line that connects the planet and the Sun, with one nestled between them and the others extending outward on either side. These points are more transient than their Trojan cousins. They're not naturally stable over long periods, but they serve a different kind of role, especially for observation. Modern space telescopes and probes often reside in these zones, using their balance to minimize fuel consumption, while maintaining a constant view of the cosmos or the planet they orbit. The Sun-Earth L2 point, for instance, is where the James Webb Space Telescope quietly orbits. It floats in Earth's shadow, shielded from sunlight and heat, gazing outward into the deep. For Mars, similar opportunities exist. L1, between Mars and the Sun, offers a continuous view of the Martian surface, perfect for solar studies or storm monitoring. L2, on the opposite side, offers a constant gaze into deep space, perhaps someday hosting a future observatory. And now, as 3i Atlas glides through this region, its fragments may well pass near these Martian Lagrange points. Some may slow slightly, some may curve, caught in a temporary balance. Most will simply drift past unfazed, their paths too steep or swift for capture. But every now and then, a fragment might pause, just long enough for its motion to match the subtle curve of the gravitational terrain, just long enough to be noticed. Astrophysicists are especially interested in these moments, not because they reveal something dramatic, but because they remind us how much structure lies hidden in apparent emptiness. Space is not a void. It is a layered, textured, gravitational landscape, one where even the faintest object, if moving just so, can find a temporary home. And Lagrange points, though invisible to the eye, are real places. In a poetic sense, they are the universe's resting spots, places where forces balance, where motion calms, where a fragment might linger before moving on. From Earth, we cannot see this pause directly. The distances are too vast, the fragments too small, but we can infer it. A slowing brightness, a change in arc, a repetition in position. These quiet clues tell us that something has entered balance, if only for a time. It's uncertain whether any of 3i Atlas's pieces will align so precisely, but the possibility is worth watching. A fragment caught in a Martian Lagrange point might stay there long enough for future missions to study. Perhaps not now, but someday. a relic of interstellar space. Suspended in a gentle saddle of gravity waiting in the dark. There is a quiet irony here, that places of perfect balance are often places of impermanence. Small nudges, a solar gust, a planetary tug, can tip an object out of alignment, and yet, even these fleeting rests are significant. They are moments of calm in a universe of constant motion. You might picture a leaf caught in a still eddy of water, circling gently just out of the current, not forever, but long enough to notice. In that image we find the character of Lagrange points. They are soft pauses, cosmic commas, they let fragments breathe. And perhaps there is something to learn from that even the smallest object given the right conditions can come to rest in a quiet place. That movement does not always mean haste, that sometimes the universe allows for stillness, not as an ending, but as a middle. So we listen. We model these points not as fixed locations, but as living regions shaped by mass and motion. We continue to monitor the fragments trailing through our atlas, and we wonder, will one find its pause there? Perhaps you're imagining it now. A tiny tumbling shard, no larger than a suitcase, slowing as it passes near Mars, then settling into a soft, slow arc. It stays there, unvisited, unseen, bathed in sunlight, casting a whisper of reflection back toward the red planet and the black beyond. It may drift on tomorrow, or next year, or in 1,000 years, but tonight it rests. Beyond the known moons of Mars, Phobos and Deimos, there may be others, fainter, quieter, smaller, perhaps only temporary, perhaps no more than fragments, barely held in orbit for a time. And as we drift with the scattered trail of Three-Eye Atlas, we begin to wonder, could one of its fragments become such a moon? Captured satellites, as they're called, are not unusual in our solar system. Many moons, especially among the outer planets, were not born beside their parent worlds. They were wandering bodies, likely asteroids or comets, that passed just close enough, at just the right speed and angle, to be caught. Caught not by force, but by balance. By motion that aligned gently with a planet's pull. Mars's 2 known moons are thought to be captured as well. Phobos and Deimos are small, irregularly shaped, and dark in colour. Their surfaces speak of ancient impacts, dust, and perhaps origin stories that begin in the asteroid belt. They orbit closely, especially Phobos, which spirals ever closer to Mars each year, inching toward a slow, inevitable breakup millions of years from now. But what about the possibility of smaller moons? Faint ones, provisional ones, fragments that may have wandered near Mars, settled into brief orbits, then drifted away again. It's a question scientists have explored before. Mars's gravity is not particularly strong, and its neighbourhood isn't as densely populated as Jupiter's or Saturn's. But that doesn't mean it's empty. Simulations suggest that small bodies can indeed become temporarily bound to Mars, sometimes for weeks or months, sometimes even for years. If one of 3 Atlas's fragments were to pass near Mars under the right conditions, it too could become a temporary satellite. It wouldn't be visible to the naked eye, it might not even be noticed for some time, but it would orbit, a silent, subtle addition to the Martian sky. Such a body would trace a looping path shaped by both Mars's gravity and the influence of the Sun. These orbits are often unstable, perturbed by the tug of other planets, or by radiation pressure from the Sun. But while they last, they tell a story of quiet capture, of slow companionship. There's something moving about that idea, that a piece of interstellar ice and dust could pass near Mars and become, for a time, its companion. Not forever, just long enough to circle, just long enough to be part of another world's rhythm. We've seen hints of such behaviour before. Earth itself sometimes captures small temporary moons. These are not the grand glowing kind we imagine lighting up the night sky. They are typically only a few metres across, barely reflective, often detected only after they've already arrived, and sometimes not until they've departed again. One of the most famous examples is 2006 RH-120, a tiny asteroid that orbited Earth for about a year before drifting away. It came and went without fanfare, a quiet visitor, just like 3I Atlas. Astrophysicists still debate how often these captures occur. Some suggest we may have small satellites orbiting Earth or Mars at any given time, too faint to detect without sustained observation. Others believe they are rarer, more fleeting, but either way they remind us that space is not static, that relationships between objects can form suddenly, softly, then dissolve again. And perhaps, as 3I Atlas and its fragments approach the Martian system, one such moment is beginning now. A piece drifts close, its speed diminishes slightly, its path curves, drawn not toward impact but toward orbit. It begins a slow loop. No one sees it at first. It casts no light, but it is there. You might imagine standing on the surface of Mars, looking up into its pinkish sky at twilight. Phobos races past overhead, fast and low. Deimos drifts more slowly, and in between them, unknown to your eyes, a third object circles, small, silent, interstellar in origin. A moon not born of Mars but claimed by it, for a little while. It's uncertain whether such a capture from 3I Atlas will happen, but the physics allow it, and the possibility, like so many in astronomy, is enough to stir wonder. After all, much of what we know about the cosmos began as a question, a maybe, a soft suggestion in the data. It's only with time and patience that these maybes become measurements, so we continue to observe. We let our instruments sweep the skies near Mars. We model the potential paths of the comet's fragments, and we dream, just a little, of moons that pass quietly through borrowed orbits, carrying with them the cold breath of other stars. Because sometimes a whisper is all the universe gives, and sometimes it's more than enough. If you've ever seen a comet streak across the sky, glowing softly with a curved tail streaming behind it, you've witnessed the gentle interplay between light and matter. These tails, so delicate, so ethereal, are not made of fire, but of dust, plasma, and sunlight's whispering touch. As 3I Atlas continues its passage near Mars, we turn our attention now to the tail it may cast and to the materials that form it. For even in silence, a comet speaks through its trail, and when one begins to fragment as 3's Atlas appears to be doing, its message becomes more complex, more textured, more beautiful. Every comet carries two primary tails, one composed of dust, the other of ionized gas. The dust tail is what we often see in photographs, a curved, glowing band of tiny particles, gently pushed away from the nucleus by sunlight itself. This tail follows the comet's trajectory, arcing behind it in soft loops. The other tail, the plasma or ion tail, points straight away from the sun, regardless of the comet's direction of motion. It is shaped not by motion, but by the solar wind, a stream of charged particles constantly flowing outward from our star. In both cases, the tails are sculpted by pressure, not mechanical, but radiant. Sunlight, though it carries no mass, exerts a tiny force on everything it touches. Over time, this pressure can push dust particles out and away from a comet's body. Solar wind, meanwhile, interacts with gas molecules in the comet's coma, stripping electrons and creating glowing ions that drift into the dark. With 3's Atlas, these processes are unfolding in real time. Its fragments may each begin to develop their own tails, some brighter, some fainter. They will stretch behind the bodies like soft streamers, too faint for our eyes, but visible through the long exposures of space telescopes and sky surveys. You might picture them now, small icy shards, tumbling silently, each one trailing a filament of dust or gas, like threads unspooling in zero gravity. Together they form a loose train, a procession of interstellar echoes, weaving their way through the Martian orbital region. and though we may never see them with our own eyes, their presence changes the light we receive. Dust scatters sunlight. Ions emit soft ultraviolet glows. Instruments designed to measure these subtle signals, like spectrographs and photometers, can reveal what the fragments are made of. Silicates, carbon compounds, perhaps even traces of water or organic molecules. In this way, each tale becomes a story. A spectral fingerprint, a silent communication from matter that has crossed immense distances, exposed to countless cosmic rays, sculpted by time and starlight. Astrophysicists still debate how much material a comet can shed before it disappears entirely. Some survive multiple orbits, losing only surface layers. Others break apart after just one pass, undone by the sun's warming touch. In the case of interstellar objects like 3I Atlas, the rules are even less clear. Its structure is unknown, its strength is uncertain, its behaviour unpredictable. But we know this: as it fragments, it becomes more expressive. Each piece interacts with light in a new way. Each curve, each flicker, tells us something about its origin and fate. What's especially gentle about comet tails is their impermanence. They are not fixed structures. They evolve from hour to hour, shifting with solar wind fluctuations, changing as the comet rotates, varying with temperature and angle. They're made of the most transient materials in space: dust grains, gas molecules, photons, and yet they linger long enough to be seen. Sometimes comets leave behind debris streams that persist for decades. These streams can become meteor showers when Earth crosses their path. Perhaps, in years to come, a small meteor streaking through our atmosphere will be traced back to one of these 3I Atlas fragments, an interstellar particle burning bright and brief in our night sky. There's a poetic symmetry in that. A comet from beyond the stars shedding dust across Mars, leaving trails that may one day kiss Earth's atmosphere. A moment of light from a journey that began in deep time. And if that does happen, the meteor won't be large, it won't roar, it may last only seconds. But to those who see it, and to those who know what it will be something precious. A meeting of two worlds across unimaginable distances. You might imagine lying beneath the stars on such a night, eyes tracing the sky, wondering if that brief shimmer was born of 3I Atlas, if it once drifted near Mars, if it once whispered against the sun's wind. So we continue to track the tails. We model their shape, their density, their lifespan. We watch how the fragments of 3I Atlas respond, not with noise, but with motion, with curves, with light. The comet does not speak, but its tails do. They remind us that even the quietest objects can leave a trace, and that in space nothing ever truly vanishes. It transforms, it drifts, it glows, and then it fades. Mars, that dusty and rust-coloured world, has always watched the sky above it in silence. No eyes there, no oceans to reflect the stars, no forests to hush the wind. But the planet has felt the passage of light, wind and dust for billions of years. Now, with 3 Atlas drawing near, its thin atmosphere prepares, in its own quiet way, to receive the brush of interstellar matter. The Martian atmosphere is faint. If you were to stand on the surface, you'd find the air pressure less than 1% of Earth's, barely enough to carry a whisper. It's made mostly of carbon dioxide with traces of nitrogen and argon. Winds blow across the sands, carving dunes and raising dust storms, but even the fiercest Martian gust is no more than a breeze by terrestrial standards. Still, when fragments of comets pass through this delicate shell of air, something beautiful happens. Even the thinnest atmosphere is enough to produce a glow, a faint exhalation of light known as an air glow, or in stronger events, a meteor trail. On Earth, we call them shooting stars. On Mars they happen too, but only rarely, and always in silence. If a small piece of 3I Atlas were to intersect Mars's upper atmosphere, it would begin to burn, gently in terms of energy, but with enough heat to create a momentary streak. It might be visible to an orbiting satellite, or even to a rover's upward-facing camera if it happened in just the right patch of sky. These interactions are more than visual, they're also chemical. As a meteoroid burns, it releases compounds into the atmosphere. Sodium, magnesium, iron, elements forged long ago and carried across deep space, become part of Mars for a fleeting instant. They add to the planet's thin halo. They remind us that Mars is not a sealed world, but a participant in cosmic exchange. NASA's Maven mission, which orbits Mars, has actually observed such events. It has recorded the subtle signatures of a meteoric deposition in the upper atmosphere, not in the form of blazing trails, but as faint enhancements in ultraviolet and infrared light, signals that tell a story only instruments can hear. So far, nothing from 3I Atlas has been confirmed as entering the Martian sky, but the possibility remains open. Some of the comet's fragments are small, so small that if they enter Mars's atmosphere they may skip like stones or disintegrate without fanfare. Others might burn, softly and briefly. A few may even survive the passage, reaching the surface as micrometeorites, dust-sized grains from another star system, now resting on Martian soil. Astrophysicists still debate the frequency and importance of such events. Is Mars regularly collecting interstellar material without us knowing? How many grains of cosmic dust settle each year on its plains and ridges? It's uncertain. Our instruments have only scratched the surface, quite literally. But there's something quietly profound about imagining a grain of dust formed around a star in another galaxy or another corner of the Milky Way, travelling across light years, then falling gently into the atmosphere of a planet it never knew. Mars, with its ochre deserts and frigid nights, becomes a receiver, not of messages in the traditional sense, but of matter, of memory, of motion that began long before we walked the Earth. You might imagine that grain now, tumbling silently through space, tracing a gentle arc, beginning to warm as it approaches the planet. It glows briefly, perhaps only for a second, then falls. It's not a meteor shower, it's not a spectacle, it's a whisper, a single note in a cosmic symphony that most ears cannot hear. If 3I Atlas leaves behind a trail rich enough, perhaps Mars will encounter more than one such fragment. Perhaps years from now, a mission will detect an unusual isotope in the dust, or a crystalline structure not found in native Martian rock. And perhaps, from that clue, we will trace a connection back to this moment, to this quiet season of passage. There is in this possibility a reminder. Not all arrivals are grand. Some are soft, almost invisible, but they matter. A molecule, a grain, a shimmer. They are the threads that sew time together. And so we watch. We let our satellites orbit. We let our rovers continue their silent wanderings across the Martian landscape. We let our instruments listen for faint disturbances in the atmosphere, moments when something not from here brushes gently against the air. Because when interstellar dust meets Martian sky, something changes. Just a little. Just enough. And in that small change, a universe breathes. Within each comet lies a kind of frozen library. Trapped beneath layers of ice and dust are ancient molecules, some simple, others astonishingly complex. As 3I Atlas glides silently through the solar system, scattering fragments near Mars, we find ourselves wondering what secrets lie locked inside its icy heart. Many comets are composed of more than just water ice and rock. Their cores often contain organic molecules, compounds built from carbon, hydrogen, oxygen, and nitrogen. Some are the very building blocks of life. Others are more primitive, never incorporated into planets or atmospheres, never warmed enough to evolve. When sunlight warms a comet's surface, some of these compounds sublimate, transitioning directly from solid to gas. They flow outward, forming a temporary atmosphere called a coma. Instruments trained on these comae, whether on Earth or in space, can detect the spectral fingerprints of specific molecules, and what they reveal is quietly remarkable. We've seen traces of formaldehyde, methanol, hydrogen cyanide, even amino acids in rare and special cases. These are not life themselves, but they are its precursors, steps along a chain that, under the right conditions, could lead toward biology. Astrophysicists still debate how significant cometary delivery was in shaping the early chemistry of planets like Earth. Did comets seed our world with the ingredients for life? Or did they simply contribute to an already rich primordial soup? The question remains open. But the fact that such molecules exist on icy wanderers suggests that chemistry is not confined to planets. It is written in the dark, and with interstellar comets like 3I Atlas, that mystery deepens. This object did not form near our Sun. Its molecules were assembled under different light, in a different cradle of dust and gravity. It may carry chemical ratios distinct from anything in our solar system. It may hold isotopes or structures that point to alien star systems, far older or far younger than our own. To study such a body is like receiving a sample from another neighbourhood in the galaxy. We don't need to send a probe across light years. The material has come to us. Unfortunately, with 3I's Atlas, we won't be able to examine it directly. It's too small, too distant, and moving too fast for any spacecraft to intercept. But we can still watch. As it sheds fragments and gas, as its coma grows or fades, we gather spectral data, glimpses of composition, hints of origin. You might imagine an orbiting telescope peering toward the Martian region, its detectors trained on the faint clouds surrounding one of the fragments. A sliver of data comes through, an emission line in the infrared, a telltale sign of carbon monoxide or acetylene or something more exotic. A researcher pauses, notes the anomaly, begins the long process of interpretation, and slowly another thread in the cosmic web is revealed. It's possible, even likely, that some of the same molecules now drifting from 3I Atlas also existed in the early solar system. They may have rained down on ancient Earth, Mars, Venus. Some may still be frozen beneath the Martian soil, waiting for a future rover to uncover them. Others may have long since decomposed under ultraviolet light, forgotten by all but stardust. Still, the presence of organic molecules on an interstellar object feels poetic. It reminds us that the ingredients for complexity are not rare. They are scattered, quietly across the galaxy. They form spontaneously in dust clouds. They hitch rides on icy cores. They drift. They wait. Some may have circled other stars. Others, like those on 3I Atlas, may have been cast out early, flung from newborn systems during violent migrations, left to wander alone. And yet they endure, cold, silent, preserved. You might picture a single molecule of formaldehyde caught within a tiny shard of ice, orbiting in silence for millions of years, then finally released by the warmth of a distant sun, our sun. That molecule, invisible and weightless, drifts into space. It is recorded by a sensor. It enters our data. And suddenly, it becomes part of our understanding, part of our story. Comets like 3I Atlas aren't messengers in the traditional sense. They bring no intentions, but they carry knowledge, stored not in language, but in chemistry. Their messages are encoded in spectra, waiting to be read. And as we watch this fragmenting visitor multiplying softly near Mars, we think of those messages, of molecules forming in the cold, of starlight shaping structure, of the quiet, patient evolution of matter through time. Because what we learn from these objects isn't just about comets, it's about the nature of the galaxy itself, about how stars give birth, how planets begin, how molecules move and change long before life ever begins to stir. So we listen to the comet's silence. We read its light. We wonder what stories lie within its vapour, and in doing so, we remember that even the coldest places are not empty. They are full of quiet potential, drifting under ancient starlight, waiting to be seen. Light moves quickly, but not aimlessly, and sometimes it carries with it more than illumination. It carries force. As 3 Atlas drifts onward and its fragments continue to stretch across the solar system, another influence begins to shape them: the sun's invisible breath, the solar wind. Solar wind is not wind in the earthly sense. It is a stream of charged particles, mostly electrons and protons, that flows outward from the sun in all directions. Born in the corona, the outermost layer of the solar atmosphere, it travels at hundreds of kilometers per second, bathing the entire solar system in a steady, whispering gale. When this wind meets a comet, it doesn't just pass through. It interacts with the gases escaping from the comet's surface, stripping away electrons, ionizing atoms, and creating what we call the plasma or ion tail. This tail doesn't follow the comet's path. Instead, it points directly away from the sun, sculpted not by motion, but by magnetism. Each ion in that tail tells a story. The colour of its glow, the way it bends and flickers, the ions it contains, all are shaped by interactions with the solar wind. And as each fragment of 3I Atlas begins to develop its own coma and tail, it becomes a participant in this quiet drama. But there's another effect too, subtler, longer lasting. Radiation pressure. Sunlight, though made of photons and not particles, carries momentum. When those photons strike dust grains ejected from a comet's surface, they exert a tiny push, not enough to be felt, not enough to be seen immediately, but over days and weeks this pressure can alter the path of small particles, curving their trajectories, widening their tails, and sometimes causing entire fragments to drift apart. You might imagine a soft breeze catching a feather in midair. Not enough to throw it, but enough to change its fall. That is what light does to dust in space. It shapes the trails we observe. It creates the sweeping, elegant arcs we see in long exposure comet images. It writes motion with light alone. For 3I Atlas, this means that each fragment is now on a slightly different journey. Those closer to the sun receive stronger pressure. Those rotating at odd angles may eject dust unevenly, producing asymmetrical tails. Some may begin to spiral gently away, even as they continue on their broad interstellar path. Astrophysicists model these effects with care. They use solar wind velocity maps, magnetic field strength, and solar radiation profiles to simulate what a comet's tail might look like in different seasons, at different distances. These models help predict where fragments will go, and how long they will remain visible. Yet even with all our models, there's uncertainty. The solar wind is not constant. It fluctuates with solar activity, coronal mass ejections, solar flares, magnetic turbulence. Some comets pass through calm regions, their tails thin and straight. Others are caught in storms, their structures twisted and blown apart. We don't yet know what 3I Atlas will encounter. But whatever it is, the results will be inscribed in the sky, in the shape of its ion tails, in the fading brightness of its coma, in the gentle divergence of its smaller companions. And as these fragments feel the sun's touch, they become even more expressive. They glow, not because they choose to, but because the laws of nature have written such beauty into their structure. Molecules absorb energy, electrons jump and fall, photons are released and light is born. You might picture one of the smaller fragments now. A piece no larger than a pebble, released weeks ago by the main nucleus. It spins slowly, its icy surface cracking in the sunlight. Tiny jets emerge, expelling gas and dust into the vacuum. The solar wind catches the ions. Sunlight pushes the dust, and all of it begins to stretch backward, forming a tiny tail, invisible to the eye, but real nonetheless. That fragment will never return. It may spiral outward for years. It may be drawn into the sun's deeper gravity well, or perhaps it will linger in the Martian system for a while, before being nudged toward the asteroid belt or beyond. Its fate is unknown, but its moment now is filled with grace, and we, watching from afar, see not just dust but story, not just plasma but passage. We see how even the lightest elements are shaped by forces we can't feel. We see how structure arises not from command, but from influence, from the soft push of light, from the magnetic arms of solar breath. Astrophysicists still debate the long-term behaviour of these comet tails, how far they stretch, how much they disperse, how they interact with planetary magnetic fields or atmospheric edges. But for now, we can simply admire them as natural flowing signatures of a comet's path through space. Each tail is temporary, each arc unique, but while they last, they illuminate the invisible, and for us, adrift in thought beneath velvet skies, they remind us that motion itself can be poetry, and that even in silence, light can sculpt a masterpiece. Far beyond Mars, beyond even the icy fields of the outer planets, lies a realm so distant and cold that sunlight becomes no more than a whisper. This is the domain of the Oort cloud, and perhaps, just perhaps, the birthplace of Three-Eye Atlas, or at least a place not so different from it. The Oort cloud is not a place we can see. No telescope has ever photographed it. No spacecraft has passed through it. It exists in the outermost edge of our solar system, between 2,000 and perhaps 100,000 astronomical units from the Sun. For reference, Neptune orbits at about 30 AU. Voyager 1, our most distant spacecraft, is just now entering interstellar space at around 160 AU. The Oort cloud lies unimaginably farther still, and yet we believe it's there. Its presence is inferred from the behaviour of long-period comets, those that arrive with highly elongated orbits, often tilted at steep angles, visiting the inner solar system once every million years or more. Their paths hint at a spherical shell of icy bodies surrounding the Sun, loosely held, easily perturbed. It's thought that the Oort cloud contains trillions of icy fragments, cometary seeds that formed close to the Sun but were ejected outward by the gravity of the giant planets during the early days of the solar system. They drifted outward, slowing until they reached the edge of the Sun's gravitational influence, where they remained. But not all of them stayed. Occasionally, a passing star, or even the tidal forces from the Milky Way itself, nudges one of these icy objects, sending it back toward the inner solar system. These are the visitors we sometimes see, ghosts from the edge of the solar family, returning after eons of cold sleep. Some scientists once wondered whether Three-Eye Atlas might be such an object. Its trajectory, however, tells another story. Its inbound path is too steep, its speed too high. It likely originated from beyond even the Oort cloud. Not a returning member of our family, but a stranger from another one. Yet the similarities remain. The Oort cloud may be local, but it is not unique. Most star systems are believed to harbour similar outer reservoirs, shells of icy fragments formed during planetary migration and gravitational scattering. In this sense, the birthplace of Three-Eye Atlas may have been much like our own distant frontier. You might picture it, a dim red dwarf star flickering in a sparse field of stars surrounded by a halo of distant frozen bodies. One of them is nudged, ever so slightly. Its orbit shifts, begins to fall inward, but misses the star entirely. Instead, it escapes. Over time, gravity loses its grip, and the object becomes unbound, exiled into the dark. That body drifts for millennia, crossing empty gulfs of space, until, by chance, it enters our solar system. Perhaps it is Three-Eye Atlas, or perhaps one of many like it, each on a lonely arc across the galaxy. Astrophysicists still debate how many such interstellar objects might exist. If every star system has an Oort cloud, and if each one loses even a fraction of its bodies to interstellar space, then the galaxy could be filled with icy wanderers, unlit, unbound, and mostly invisible. Most would be undetectable. They don't glow, they don't pass close, but every so often one does. Like one Oumuamua, like Tam Borisov, and now like 3 Atlas. These objects may carry within them the same materials as our own comets, silicates, volatiles, perhaps even organics, or they may be subtly different, shaped by the chemistry and radiation of other systems. Measuring those differences is part of the scientific dream. Each interstellar object is a potential sample return, except the sample comes to us. In 2023, scientists proposed the idea of rapid response missions, spacecraft launched in short order to intercept and study future interstellar objects. Such missions would aim not just to observe, but to collect, to touch, to analyze. But for now, we must settle for observation from afar. Still, even from a distance, 3i Atlas connects us to the wider galaxy. It reminds us that the solar system is not isolated, that our sun has neighbours, that matter moves between stars, slowly, quietly, inevitably. Perhaps the Oort cloud is not just a boundary, but a bridge. You might imagine standing on Pluto or beyond on a moonlit ridge of ice, watching the stars from the edge of our system. Somewhere out there, far beyond the Kuiper belt, a shard of ice tumbles inward. Not from here, not from our sun, and yet it is coming. The comets we see may be local, but their behaviour, their silence, their fragility, their drift is universal. Whether from the Oort cloud or beyond, they follow the same physics. They reflect the same sunlight. They whisper the same truths. And 3 Atlas, as it scatters its fragments near Mars, may have begun its journey in a place not so different from the outer edge of our own system. A cold, dark sea of icy bodies. A quiet frontier. A waiting place for motion yet to come. As 3i Atlas glides closer to Mars and its fragments multiply across the night, we pause now to look deeper, not at the comet itself, but at the fabric of space through which it moves. A fabric stretched and stained by time, one marked by redshift. Redshift is not a thing we see directly with our eyes, though it's all around us. It's a shift in the light of distant objects, galaxies, quasars, even the cosmic microwave background, as they recede from us. The farther they are, the more stretched their light becomes, sliding toward longer wavelengths, toward red. It's how we know the universe is expanding, how we know that galaxies are drifting apart, how we measure deep time. But there's more to redshift than expansion. It's also a kind of clock, a soft record of motion through space-time. When we look at the light from a distant galaxy and find it stretched, we're not just seeing distance, we're seeing age. We're seeing the journey that light has taken, perhaps for billions of years, across the shifting weave of the cosmos. And though 3 Atlas is close by in comparison, its movement echoes that same slow drift. Its fragments move not through empty space, but through red-shifted memory. A universe in constant expansion, even at the smallest scales. The photons we use to detect 3i Atlas, the ones that reflect off its icy surface, don't redshift significantly in our frame. They arrive quickly, from just a few astronomical units away, but the light all around them is different. The background sky, the field of ancient galaxies, the glow of the cosmic microwave background, all of it carries redshift. All of it tells us where we are and when. You might imagine space itself as a great sheet stretching slowly, endlessly. On that sheet are objects, some near, some impossibly far, each marking a point in both space and time. As the sheet expands, the points move apart. Their light drawn across the ever-widening frame becomes fainter, redder, older, and into this frame enters 3i Atlas, a fragment from another system, its atoms shaped by forces far away, now moving through the geometry of our space. It is not part of the distant red-shifted galaxies, and yet it is caught in the same stretch. its motion is local. But the space it occupies is not. Astrophysicists sometimes speak of cosmological redshift and gravitational redshift, the first caused by the expansion of the universe, the second by the warping of space-time near massive objects. In both cases, light changes, not in speed, but in wavelength, in tone. And while we usually apply these concepts to distant galaxies or black holes, they shape even the quiet motion of objects like 3i Atlas. Not in ways we can directly measure from Earth, but in the way they remind us. Everything moves within a changing frame. Everything that drifts within time as much as space. Perhaps you're lying back now, imagining the sky above. Imagine each star not just as a point of light, but as a story of movement. Each glow a delayed message, redshifted by expansion, or bent by gravity, or cooled by age. Some stars have long since died. Some galaxies have moved farther than we'll ever reach, and yet their light is still arriving, shaped by the stretch of time itself. And just as redshift helps us see the past, it also helps us understand where things are going. The same equations that describe the expanding universe also let us model the future. We can predict how light will stretch, how structures will drift, how temperature will fall. The cosmic microwave background, that leftover whisper from recombination, has cooled over billions of years, from thousands of degrees to just 2.7 Kelvin. A soft, invisible blanket that now hums quietly across the sky. 3i Atlas moves through this light. It does not interact with it, not directly, but it carries within it atoms that have experienced billions of years of cosmic background radiation. It is a body built beneath redshift. Its entire existence has been shaped in a universe that stretches, and so, in a way, the comet is not just a fragment of matter, it is a participant in the story of time. Astrophysicists still debate the limits of redshift as a measure. Does the fabric of the universe stretch indefinitely? Will light fade into irretrievable wavelengths, forever beyond detection? Or will some deeper structure reveal itself, something not yet seen, hidden beyond the veil of our current understanding? It's uncertain, but as we track this small interstellar object through our local sky, we're reminded of the broader context, of the ancient light behind it, of the stretched photons that bathe it, of the deep time into which it moves. Because redshift isn't only about what's far, it's about how we listen, how we understand motion and age, even in the faintest signal. And tonight, as we rest beneath the stars, we know that even here, even now, we're watching things change, slowly, softly, redshifted by time. The solar system, for all its elegance, is not a simple clockwork. It's a web of influences, gravitational slopes and bends, invisible tugs and pushes. And now, with 3i Atlas drifting nearer to Mars, we shift our focus to the quiet sculptors of celestial motion, gravity wells. Every planet, every moon, even every fragment sits within a gravity well. You might imagine it like a curved depression in space carved by mass. The heavier the object, the deeper the well. The closer you are to its centre, the more you must resist to climb out. It's not a well of stone or steel, but of space-time itself, bent gently by presence. The Sun's well is the deepest in our solar system. Planets orbit within its grasp, held not by force in the traditional sense, but by geometry. Mars has a well too, shallower than Earth's, but deep enough to shape the path of passing dust, debris or comets. Even 3 Atlas, though moving fast and largely unbound, feels the subtle gradient of these wells as it flows past. And between these wells, along the invisible contours of the system, lie regions of gentle influence, places where gravity overlaps, cancels, or reinforces itself in curious ways. Some of these are barriers, others bridges. It's along these bridges that comets often travel, especially when they're not native, when they arrive from afar, passing quickly through. As 3 Atlas approaches the inner solar system, it threads a path between multiple wells, first feeling the long draw of the Sun, then the modest pull of Mars, then briefly, the gravity of Earth and its moon. Each mass bends the trajectory slightly, curves the path, adds or removes a whisper of momentum, and if fragments multiply, as they seem to be doing, each piece will feel those wells differently. A larger piece may swing wide, while a smaller one dips inward. Some may cross into temporary capture. Others may spiral away, nudged outward toward Jupiter's vast domain. In this way, gravity wells do more than hold. They sort, they guide, they filter the possible futures of passing objects. You might imagine space as a gently undulating surface, like a frozen lake made of glass. The wells are dense in the surface, some wide, some steep. A marble rolled across the glass will curve naturally toward the deepest parts. It may circle them, it may fall in, or it may pass close, its path subtly bent. Multiply this by 1 billion marbles, and you begin to see the quiet traffic of the solar system. Astrophysicists often model this behavior in terms of the 3-body problem, a classical conundrum in orbital mechanics. How do 3 massive bodies, say the Sun, Mars, and a comet fragment, interact over time? The answer is complex, even chaotic. But patterns do emerge. Some fragments of 3I Atlas may follow predictable arcs, slipping between wells like beads on an invisible thread. Others may experience gravitational assists, a slingshot effect, gaining or losing speed as they pass near planets. A few may even collide with existing objects, not in fiery explosions, but in quiet impacts that leave only chemical traces. This idea, of quiet capture or redirection, leads us to the concept of gravitational keyholes. These are tiny regions in space where a passing object, if it moves through at precisely the right moment and angle, will be redirected in future orbits to intersect a planet. It's like threading a needle from 1 million kilometers away. Most comet fragments never pass through these keyholes, but every now and then one does, and when that happens, it sets in motion a chain of events that can span decades. Could one of 3I Atlas's fragments enter such a path? It's uncertain. We model trajectories, but uncertainty builds over time. A small force, radiation pressure, solar wind, gravitational tides, can push a fragment off course. Still, the possibility invites observation, and if a fragment does pass near Earth's well, or Mars's, or even Jupiter's, it could become bound. Not permanently perhaps, but long enough to be observed again, long enough to become part of the solar story. You might picture a single piece now, small, dark, tumbling. It skirts the edge of Mars's gravitational well, curves slightly, gains speed, then flows outward again. It may return in a few decades, or it may not. But the well has touched it. Its path is changed. Gravity, in this sense, is less like a force and more like a conversation. Each object responds to the space it enters. Each well speaks in curves, and the objects that pass through, whether icy comets or scattered dust, carry those curves forward, altering the harmony in subtle ways. Astrophysicists still debate the full extent of gravitational interaction in loosely bound systems. Some suggest that small fragments, especially interstellar ones, may skip between multiple planetary wells before being lost again to deep space. Others argue that the chaotic motion makes prediction difficult past a certain window, but all agree that the dance is beautiful. So we watch, we map wells, we simulate paths, and we let ourselves wonder what new stories these fragments might write, not only across Mars's skies, but across the long reach of time. Because in the end, a gravity well is not a trap. It's an invitation, and every object that answers it becomes part of the quiet choreography of our ever-moving sky. The universe is stitched together by threads we rarely see. Galaxies not scattered randomly, but instead connected by vast filaments of dark matter, gas, and stars, an immense architecture known as the cosmic web. Tonight, as we trace the multiplying fragments of 3i Atlas near Mars, we widen our view and reflect on the hidden geometry that links all motion, from the grandest scales to the quietest trails. The cosmic web is the largest known structure in the universe. Stretching across billions of light years, it resembles a vast lacework. Strands of matter connect dense nodes where galaxies cluster, while in between lie enormous voids, silent and empty. Gravity sculpts this web, slowly, patiently, drawing together material in filaments, feeding the growth of galaxies from the dark. And while 3i Atlas moves through our solar system, a speck within a speck, it too is part of this structure, not in scale, but in principle. Its motion is shaped by gravity, by proximity, by the invisible pull of surrounding masses, just like the galaxies. We tend to think of interstellar objects as solitary travellers, but even solitude has a context. 3i Atlas was once part of something, perhaps a protoplanetary disk, perhaps a larger body that fractured long ago. Its fragments, now multiplying, echo that ancient past. A tiny version of the same fractal patterns we see in the cosmic web, nodes breaking apart, filaments forming, structure emerging from motion. In this way, the trail of debris behind 3i Atlas is not unlike a miniature filament. Each fragment moves with its own speed, its own vector, but all share a common history. Their paths may diverge, but for now they remain loosely connected, like stars within a stream or galaxies within a cluster. Astrophysicists still debate the full extent of structure at small scales. Do debris trails from comets exhibit the same gravitational clumping we see in galactic clusters? Can small particles be shepherded into filaments by solar tides, by planetary gravity, or even by electromagnetic forces? The answers are emerging slowly, like stars forming in dust. One curious parallel is found in the behaviour of tidal streams, those long ribbons of stars pulled from dwarf galaxies as they are absorbed by the Milky Way. These streams stretch across the sky in delicate arcs, shaped by the same gravitational dynamics that influence passing comets. And just like the fragments of 3i Atlas, they tell a story of disassembly, of quiet loss, and of continued connection. We also see similar patterns in planetary rings. Saturn's rings, for instance, are not just uniform disks. They contain clumps, waves, spirals, structures formed by resonances, by shepherd moons, by complex gravitational interactions. Even in these thin sheets of dust and ice, we find echoes of the cosmic web's logic. So perhaps the multiplying trail behind 3i Atlas is more than just debris. Perhaps it's an emergent shape, a kind of cometary filament sculpted by solar wind and gravity, growing fainter the farther it stretches, but still coherent, still whole. You might imagine a thread stretching behind the comet dotted with tiny jewels of dust and ice. Some drift slowly, some spin gently. All are bathed in sunlight, and all are moving, some toward Mars, some away, some on paths that will carry them beyond Jupiter, Saturn, perhaps even back into interstellar space. This slow unravelling mirrors the larger unravelling of matter throughout the universe. The cosmic web is still evolving, galaxies are still clustering, voids are still growing. And even here, in the inner solar system, comets are still falling apart, still seeding trails behind them. Each fragment of 3i Atlas is like a node on a thread. If we could map their trajectories over time, we might see patterns emerge, delicate chains, intersections, arcs. Perhaps one will drift toward Mars's orbit, another toward the asteroid belt, another may linger, then return in centuries hence, long after our own technologies have changed. And all of it begins with a fracture, a quiet one. Astrophysicists sometimes refer to this kind of structure as hierarchical. Small patterns reflect large ones. fragments reflect clusters, trails reflect filaments. A comet's debris field can, in a way, mirror the very shape of the universe. It's a humbling idea that in a tiny fragment of interstellar dust, we might glimpse the same logic that shaped the galaxies, so we continue to observe, to map, to wonder. Not just because 3i Atlas is passing close, not just because its fragments are multiplying, but because every fragment tells a story of connection, of structure, of the quiet order beneath apparent chaos, and in that order we find beauty. Because even the smallest trail in space can echo the shape of everything. When we think of signals in the sky, we often imagine dramatic pulses, blazing flares from supernovae, rhythmic beacons from pulsars, or the sudden flash of a gamma-ray burst. But the universe also speaks more softly, in faint glimmers, in momentary flickers, in quiet anomalies that last just long enough to raise a question. Now, as 3i Atlas and its fragments drift through the solar system, we wonder, might they leave behind a signal of their own? Not one of intention, but one of consequence, a subtle shift, a transient glow, something small but strange. Astronomers call these phenomena transients, short-lived events that brighten or shift unexpectedly in the sky. Most are natural, some remain unexplained, and once in a while a signal appears where none was expected, brief, silent, and unrepeatable. It's possible that fragments of 3i Atlas, passing near Mars or through interplanetary space, could interact with fields, dust, or solar wind in such a way that they produce tiny measurable effects. A faint radio blip, a change in polarization, a brief streak of ionized gas reflecting more sunlight than expected. Individually, such events might go unnoticed. But in the quiet archives of sky surveys, in the long digital exposure of time, patterns can emerge. Already some observatories scan the skies continuously for such phenomena. Projects like Pan-STARRS, the Zwicky Transient Facility, and the Vera Rubin Observatory, soon to begin full operations, are designed to catch every flicker, every motion, every whisper. Their algorithms look for deviation, for motion, for light that wasn't there before. And in those terabytes of data, perhaps one fragment of 3i Atlas will leave its mark. A brief flash, a single pixel that brightens, then fades. A curve that doesn't match the stars around it. Astrophysicists still debate the origin of some unexplained signals. There are known sources, stellar flares, distant quasars, artificial satellites, but there are also those that defy immediate explanation. Could a fragmenting interstellar object contribute to this quiet background? It's uncertain, but the possibility is enough to listen more closely. One form of signal that intrigues researchers is the meteor flash. When a small body enters a planet's atmosphere, especially a thin one like Mars's, it can produce a transient optical signal, brief but detectable. The ExoMars Trace Gas Orbiter, orbiting the red planet, has the sensitivity to detect such events. It scans for light, chemistry, and motion, hoping to capture the brief glow of entry. If a fragment of 3i Atlas were to enter Mars's atmosphere, even if only a meter across, it could produce such a flash. Perhaps just once, perhaps never again. Other possible signals are electromagnetic in nature. Comets, as they pass through the solar wind, can produce radio emissions. These emissions come from charged particles moving along magnetic fields, interacting with the coma or the tail. They're not strong, not like a pulsar's beat, but they are real, measurable, and they carry information. Perhaps one of the fragments tumbling through the solar wind produces just such a radio emission. Perhaps it intersects a stream of plasma, creating turbulence or eddies. Perhaps an Earth-based radio array catches a spike, a curious pattern among the background hum. Or imagine something even quieter, a gravitational micro-lensing event. When a small body passes precisely in front of a distant star, its mass can bend the light slightly, causing the star to appear momentarily brighter. Most microlensing events involve larger masses, planets, black holes, stars, but in theory, a compact fragment could cause a very small lensing signature. Would we see it? Probably not, but still, we model such possibilities. We imagine them. Because in the quietest regions of data, sometimes we find the most curious questions. One recent area of speculation involves fast radio bursts, brief, powerful signals from deep space. They remain largely unexplained, though some are now traced to magnetars or neutron star mergers. Others remain mysterious, and though it is unlikely, some theorize that interstellar objects moving through magnetized plasma could, under extreme conditions, trigger localized emissions. It's a reach, but science often begins with such reaches. 3 Atlas is not expected to create anything so dramatic. Its trail is too thin, its fragments too small. But in the world of cosmic signals, small does not mean silent. You might picture an observatory dome at night, its telescope slowly panning the sky, instruments humming quietly. The sky above appears still. But within that stillness, countless motions are unfolding. A tiny comet fragment moves across the sensor. A data spike registers. A flag is raised. Not as an alert, but as a gentle question. Was that something? And perhaps it was, because signals are not always sent. They are sometimes left behind, like footprints in dust, or ripples on a pond. 3 Atlas and its fragments may leave no lasting monuments, but they may leave traces, flashes, shifts, small anomalies in the rhythm of the sky, and we, with our instruments, with our questions, are here to listen. Because in a universe made of light and motion, even a single moment of difference is worth noticing. For most of its journey, 3 Atlas has been cold. Not simply cool, but deeply, cosmically cold. Its core untouched by sunlight, its surface insulated in vacuum. And yet now, as it ventures closer to the sun and fragments near Mars, warmth begins to seep in. The warming of a comet is not sudden. It is soft and slow, like the first rays of dawn melting frost on stone. As sunlight begins to touch its surface, the outermost ices start to sublimate, turning directly from solid to gas. Gases bloom into space, carrying dust with them, forming the coma and sometimes tails. But beneath that surface lies mystery, what warmth might reveal, and what may still remain hidden. Could fragments of 3I Atlas contain internal pockets, insulated regions that hold ancient chemistry? Could they shelter, for a brief time, ingredients or processes that we normally associate only with larger worlds? Astrophysicists still explore this question, especially as it relates to cryovolcanism, a process seen on distant moons like Enceladus and Europa. On those worlds, internal heat, generated by tidal flexing or radioactive decay, causes subsurface oceans to form beneath icy crusts. In those oceans, complex chemistry unfolds, shaped by energy and time. Now, 3I Atlas is no moon. It's far too small to sustain tidal heating or long-lived subsurface activity, but within even the smallest bodies, warmth changes things. Heat flows inward, ices begin to shift, pockets of gas may build up pressure, causing jets or vents. Chemical bonds break and reform, and so, as its fragments warm, we wonder, what hidden substances might be released? Could they include more than carbon dioxide or water vapour? Could they offer hints of ammonia, methane, even complex organics that formed around another star and survived the interstellar journey? We've seen such richness before. Comets in our solar system have released cyanides, hydrocarbons, alcohols. Some have even shown amino acid precursors. These molecules are fragile. They degrade in radiation. Yet when sealed in cold darkness, they persist. If 3i Atlas originated from a protoplanetary disk around another star, its material may reflect a different chemistry, a different history of heat and light. It may have formed near an M-dwarf, or perhaps a star long gone, and if so, its fragments are not just pieces of rock and ice, they are samples from another environment, preserved in cold for perhaps billions of years. Now, as those fragments approach Mars and the inner solar system, they're exposed. They begin to release vapours, not in bright explosions, but in soft sighs. Jets may form, a fragment may spin. The coma may shift colour as different gases take their turn in the light. It's uncertain how much warmth each fragment can hold. Their size, their rotation, their albedo all shape how sunlight is absorbed. Some may warm quickly, others may remain cold for much longer, especially if their surfaces darken with dust. And beneath the surface, temperatures change slowly. There are thermal lags, delays between the sunlight we see and the heat that reaches inward. In some cases, this leads to outbursts. A pressure builds silently, until the crust ruptures, releasing gas and dust in a sudden plume. You might imagine such a moment now. A small fragment, turning slowly, sunlight creeping across its surface. For days, there is nothing. Then a soft crack forms, a vent opens, a fine mist escapes, stretching briefly into space before fading into the solar wind. The fragment shudders slightly, then continues, changed. Some researchers speculate that such activity could even shape a fragment's future. Outgassing can act like a thruster, pushing a comet off course. Over time, it alters the orbit, slightly, gently, but enough to matter. Could a fragment of 3i Atlas be steered this way, pushed toward a Martian Trojan point, nudged into a new arc? The answer depends on many things: mass, spin, composition. But the possibility adds another layer to the mystery. Because warming isn't just about melting, it's about transformation. It's about awakening ancient material and watching what it becomes when light returns. You might picture these fragments as frozen letters from the deep past, inked in chemistry, sealed in ice, waiting for the warmth of a star to be read. Each one holds a sentence, a phrase, a word from another system, not life, but perhaps something that once stood beside it, or something that never had the chance. We may never hold these fragments, they may never fall to Earth, but as their vapours drift, as their shapes shift, we can read them, light by light, molecule by molecule, and in doing so, we glimpse the quiet potential hidden even in the coldest corners of the cosmos. Because even in deep freeze, the universe is still writing. There is a kind of fading that doesn't announce itself. No sound, no blaze, just distance and time, quietly stretching a story until it becomes thin and difficult to follow. That's the kind of fading we now consider, as the trail of 3i Atlas begins to scatter across space. Its fragments, once closely grouped, are now beginning to drift. Not from chaos, but from natural separation. Differences in mass, spin, radiation pressure, and gravitational influence causing their paths to diverge. The result is a slow unravelling, a widening of the trail, a quiet dispersal that may go on for centuries. This is how many debris streams behave. They begin with a single event, often a breakup, sometimes a close pass to the sun, and over time their pieces stretch across millions of kilometres. The larger fragments may retain shape, the smaller ones become dust. Eventually the stream becomes a memory, detectable only by subtle meteor showers or long-term changes in reflected sunlight. It's likely that 3i Atlas is undergoing just such a transition. Not all at once, not visibly, but steadily. Its companions are spreading. Their relative distances are increasing. Some will stay near Mars's orbital path for years. Others will drift outward, perhaps toward the asteroid belt. Perhaps beyond. Astrophysicists model these dispersals using n-body simulations, calculations that track the gravitational influence of multiple bodies over time. These models show that even small forces, like the solar radiation pressure we explored earlier, can have meaningful effects. Given enough time, a cluster becomes a line becomes a cloud, and the cloud becomes indistinguishable from the background of the solar system. But even as the trail fades, it leaves echoes. Some of those echoes are physical: micrometeorites, spectral fingerprints, subtle enhancements in dust density along certain orbital paths. Others are observational data points like curves, positional archives, and still others are imaginative, the stories we tell about an object that arrived from nowhere, multiplied quietly, and left its signature behind. There's something bittersweet about this stage. The moment of maximum visibility has passed. The fragments are growing dimmer, the structure less coherent. It's as though the comet has finished speaking, and now its voice is trailing off into the dark. And yet, we keep listening. Because this is where much of astronomy lives. Not in the flash, but in the trace. Not in the moment, but in the memory. Long after a comet is gone, we can still model its influence. We can still detect its presence in the faintest data. And sometimes we find surprises. Some meteor showers on Earth are caused by ancient comets whose nuclei no longer exist. The Perseids, for instance, are the long-lived dust trail of Comet Swift-Tuttle. The Leonids come from Tempel-Tuttle. These showers persist for centuries, even millennia, maintained by the delicate spacing of dust particles along their orbits. Perhaps one day, the fragments of 3I Atlas will form such a stream. Perhaps Mars, or even Earth, will cross that path again, passing through the remains. It may not happen soon, it may never be seen, but the possibility is always there, folded into the quiet mathematics of orbits and time. You might picture a future sky, decades from now, maybe more. A faint streak crosses the Martian night. A dust particle, smaller than a grain of sand, enters the atmosphere and burns away in silence. Just a blink. But that grain may have come from 3I Atlas. A final whisper from a journey that began between stars. Astrophysicists still debate how long such fragments persist. Some are destroyed quickly, by sunlight or collision. Others remain in orbit for thousands of years, gradually breaking down. Some become part of the interplanetary dust cloud, a diffuse veil of particles that fills the solar system and glows faintly in the zodiacal light. In this way, the remains of 3I Atlas may become part of the background, no longer distinct, no longer trackable, but still there, still part of the slow drift of everything. And that too is a kind of legacy, because in space, nothing disappears completely, it only spreads, it only fades, and in the fading it becomes something else, part of the haze, part of the rhythm, part of the quiet light that fills the gaps between planets and stars. So we watch as the trail loosens. We note its positions, we update the models, we adjust our telescopes to track what remains, and then, eventually, we let it go. Because the universe is full of arrivals, but it is also full of departures, and each one leaves a shape behind, even if only for a moment. We followed 3I Atlas from its quiet arrival into the solar system, past its gentle fragmentation near Mars, through the subtle interactions with light, gravity and heat. Now we drift into the final space between knowledge and wonder, the edge of what we can see and what we simply sense. There's a kind of stillness that follows a passing, not an absence but a breath, a pause where something once moved, once glowed, once altered the rhythm of the sky. That's where we are now, watching the last of 3I Atlas's trail stretch thin and wide across the solar system. Above us, Mars orbits silently. Its path continues unchanged, save for the invisible dust and fragments that now share its region. Perhaps one of those fragments has nestled into a Trojan point, or slipped into a temporary orbit, or passed unnoticed near a quiet moon. Perhaps one is still glowing faintly, its surface warming just enough to release one final exhale of gas. And beyond, the rest of the trail scatters. Some fragments drift outward, some spiral inward. Some may one day pass Earth. Others will vanish into the soft halo of dust that surrounds the inner planets, becoming part of the sky's unending hush. But the comet's story doesn't end with its fragments. It lingers in motion itself. In the knowledge that something from outside, the third interstellar object we've ever recorded, came this close enough to be seen, measured, remembered. What makes this more than a passing curiosity is not how bright Atlas was, or how many pieces it shed, but how gently it reminded us of the galaxy's quiet traffic, of the countless objects moving through space, unnoticed, of the invisible architecture that binds and guides them, of the fact that, in deep time, paths always cross. Astrophysicists still debate what these encounters mean in the long scale. Are interstellar visitors like Three-Eye Atlas rare? Or are we simply just beginning to notice them? As our surveys grow more sensitive, we may discover dozens, even hundreds more. Some may pass close, some may break apart, some may be captured, briefly joining our solar system before departing again. And some perhaps will tell us something we didn't know before, about matter, about chemistry, about how systems form and fracture, maybe even about life's prerequisites, carried in carbon chains and icy pockets across galactic arms. But for now, Three-Eye Atlas is retreating. Its velocity is still great enough to escape the sun's gravity. It will not be captured. It will not return. It's already begun its outbound curve, ascending away from the plane of the planets, returning to the dark between stars. Its trail remains behind for a while. A widening string of icy beads, each one on a unique path, each slowly dimming, scattering, transforming. They are not lost, they are continuing, and so are we. Because what we do, what all astronomers and dreamers and stargazers do, is trace the temporary. We follow motion until it becomes memory. We listen for a flicker, we map it, we wonder, and then we wait for the next. You might picture the night sky now, with Mars low on the horizon and stars glinting faintly overhead. Somewhere near the red planet's path, a few of Three-Eye Atlas's fragments still move. You cannot see them, no one can, but they are there, carrying within them the dust of another system, another star. And as they continue their quiet drift, they carry with them our gaze, because looking up is a kind of joining. And now, as this part of the sky begins to fade back into silence, we simply breathe. Now, we settle into stillness. The trail has passed, the fragments have scattered, and the sky once again holds its hush. But something remains, a quiet thought perhaps, of objects moving between stars, of icy fragments carrying stories across light years, of how even the faintest comet breaking softly near Mars can remind us of scale, of time, of the gentle drift that connects everything. Tonight we traced a single object's journey. We followed Three-Eye Atlas through the slow unfolding of its path, its glow, its breakup, its brief nearness to Mars, and its long, quiet departure. And in doing so, we found echoes of the whole cosmos, of the recombination era, of gravity's slow balance, of the cosmic web, of redshift, warmth, tail light, and the stretch of time. Even the coldest places carry potential. Even the loneliest paths carry memory. So, if you're still with us, eyes closed, thoughts adrift, know that you too are part of this unfolding. You're stardust in motion. You're orbiting the same star that once caught a visitor from beyond. And your stillness now is just another part of the dance. Let the breath slow. Let the thoughts fade. There is no need to hold on. The sky is wide. The motion is gentle, and sleep like starlight comes when we least expect it. Sweet dreams,